So welcome to this course in Advanced Computer Architecture, or AVDARK, which is the Swedish acronym for the course. My name is Erik Hagersten. I'm a professor in computer architecture at Uppsala University in Sweden. My background is that I've been going back and forth between industry and academia about 7 times in my career. Every time you make that move, it's equally interesting. And it's not that unusual, actually, in our subject that people mix insight of research with really building products. And that's what I've been doing throughout my life. On this course, I'm going to have 2 people helping me, Andreas Sembrant and Mahdad Davari. They're going to be teaching assistants, and they're going to be responsible for the hand-in assignments as well as for the labs. There is a book called Computer Architecture, A Quantitative Approach, the 5th edition, and it's written by John Hennessy and David Patterson. It's really an excellent book. It's really needed if you would like to make this your main topic, or if you want to do really well on the exam. But just for passing this course, I regard it as optional material. There are 4 lab assignments in this course, and all of you have to pass all those assignments. There is 1 extra bonus assignment for each lab, and if you pass that one, you will earn extra bonus points. There are also 4 hand-in assignments that you do on your own at home, and these are optional. But if you complete them with some reasonable accuracy, that will also earn you bonus points for the exam. The exam is a closed book exam at the end of the course, and you can earn a maximum of 64 points on the exam. And if you gather all the bonus points in this course, that will give you exactly what's needed to pass that exam. In a nutshell, this course will cover 5 different subject areas, or 5 different batches. We'll start by talking about the memory system, so caches, optimizations, virtual memory systems, and so on. The second batch will deal with the concepts and the basics behind multiprocessors, and more importantly, we will cover how shared memory multiprocessors are implemented. So we'll talk about coherence, memory models, scalability, and so on. Then we move on to how you build really scalable multiprocessors. So we talk about some more scalable ways of doing coherence and memory models, synchronization, as well as how you build clusters. At the tail end of this course, we will start to look at how the CPUs are built. And this is sort of backward from, for example, how the book describes this subject, but I regard the first 3 batches as the more important these days. So in the first batch, we will talk about the pipelining, scheduling, superscalers, VLIWs, and so on. And at the end of the course, a couple of last lectures, we will widening the views. So we'll talk about futures, we'll talk about the state of art right now, we'll talk about GPUs, talk about dark silicon, and so on. So on the first 4 batches are structured in the same way. First, I will provide you with some recorded online lectures where I teach you the basic facts. And the idea is that you will be able to learn these basic facts at your own leisure at home when you have time to do so. During these recorded lectures, there are some quizzes. So you have some questions with some number of options as the correct answers, and you should of course do your best to answer those quizzes. But it's more a test for yourself to see if you have grasped what's been going on so far in the lecture, and allow you to actually rewind if you don't feel that you do good at these tests. There's also a question button on the screen where you can press this button at any time of the lectures and ask me specific questions that relates to that slide. Maybe there's an error on the slide, or maybe there's something you do not understand. There's also a confused button, so if you simply don't understand what I'm talking about, press the confused button, and that will tell me how much of the material that you were able to grasp. All these quizzes, the questions, and the confused clicks are anonymous. So I will not be able to see which one of you answered all the quizzes wrong or which one of you asked stupid questions. Because there, first of all, there aren't any stupid questions. And this is also to make sure that you are really, really sure that this will not affect in a way the way you graded in this course. I want, of course, for you to ask questions all along to tell me what's hard and what's easy. If you have watched all these lectures of each batch before some certain deadline, then you are up for the hand-in bonuses. There are also two in real life lectures or classes for each one of these batches. We will cover the confusions and the questions that most of you have raised during the lectures. We will also cover some more complex issues that I feel cannot be taught in an online lecture. More of kind of discussion topics. We will have some more complex exercises and in-class examples where you will try to do lots of these kind of exercises on your own. These questions are also very similar to the more complex questions that will turn up at the exam, so it's a good way to prepare there as well. You also will have to attend both of these in real life lectures for each batch in order for you to be eligible for the hand-in bonuses. There is one optional hand-in, and you have to complete that with some reasonable accuracy before a deadline, and that's the third part that you need to complete to get the hand-in bonus for that batch. There is also one mandatory lab for each batch, and this mandatory lab of course relates to the subject that we cover in the batch of that lecture. You will have to complete this mandatory, so you will have to complete each lab. The lab starts with a lecture telling you what the lab is about and instructing you how to be successful. That lab preparation lecture slot may also cover some confusions and questions that you have raised. There is also a lab preparation slot where there are no teachers available, but we have booked a computer lab for you, so you can get an early start on the bonuses. You can start to try out the lab assignments on your own. And then there are 3 physical slots, each one of 4 hours. So we have 3 different groups, A, B, and C, that will do the labs at one of these slots. And you will have to demo the labs for the lab teacher at these occasions in order for you to pass the lab. You will also have to do the extra assignment during the lab if you would like to get the bonus lab point, and for that you will also have to attend the lab preparation lecture. So in summary, there are 4 labs, there are 4 bonus assignments, and there are 4 per lab, and there are 4 hand-ins that also will earn you bonus points. And the written exam at the end, for each bonus that you pass, you get 4 points guaranteed at the exam. So there is a corresponding question at the exam that you don't have to answer for each one of these bonus items. So you get 32 points and you will pass the exam. So for more information, there is a course webpage where you know get some of the schedules. I will keep the slides there. I will keep it is a directory with papers that we refer to during the lectures. You will find the hand-in assignments, and you will find the lab assignments there. There are some reading instructions for the book, as well as some previous examples of exams that we have given in this course. So the goal of this course is very much to understand how and why of many different aspects of computers. So how and why pipelines, memory organizations, and virtual and physical memories are designed the way they are. How and why multiprocessors are built, so that this is where the coherence, the memory models, and synchronizations come to play. How and why parallelism is created and leveraged. So we'll talk about 3 kinds of parallelism: instruction level parallelism, memory level parallelism, and thread level parallelism. Also, understand how and why multiprocessors can combine many different kinds of parallelism in one design. For example, SIMD and MIMD kind of parallelism. Talk about how graphics processors or GPUs are made, as well as vector processing. You will also need to understand how computer systems are adopted for different usage area. A general purpose processor or system will not necessarily look the same as an embedded processor. And finally, you need to understand the fundamental limitations of modern computer systems. Bandwidth, energy, and cooling are a couple of examples of those limitations. And of course, that is what is driving computer architecture as a whole. So welcome to this course. I'm really going to enjoy teaching this online version of the course, which I'm actually doing for the first time this year. So please bear with me when I try to make these recordings.